Hi, good morning Lizzie.
Good morning, Dinayah.
Did you know that last week's Smart Icon provided a lot of additional knowledge, especially for those of us who still need a lot of knowledge outside of campus hours?
Oh yeah, wow, I regret not attending that seminar last week.
Today I will explain to you what I got from the Icon Smart seminar last week.
Please, I happened to not take part in the Icon Smart seminar last week.
From Professor Dr. Saya Negami, Professor in Honor and Doctor of Science Topological Graph Theory, Math Education, Yokohama National University, Japan. Saya Negami, born in 1957. He was graduated in Tokyo Institute of Technology. He was Dean of Faculty of Environment and Information Sciences from 2014 to 2018 and working as Executive Director and Vice President for Education and Publicity from 2019 to 2020 in Yokohama National University. He is a mathematician which is a pioneer of topological graph theory in Japan and working for reformation of mathematics education. Research field: topological graph theory, graph coverings and their applications under the theme data optimization for instrumentation physics, food security, and energy sustainability. How about AI? Saya Negami Dr. and Professor in Honor, Yokohama National University, Japan. Parallel computing. Graph coverings can be used to model and optimize parallel algorithms. They help distribute tasks across processors while minimizing communication overhead. Cryptography. In some cryptographic protocols, graph coverings are employed to distribute secret keys securely among multiple parties. Types of coverings. Regular coverings. These are coverings where each vertex in the base graph has the same number of pre-images in the covering graph. Regular coverings have applications in network design and coding theory. Galois coverings. In algebraic graph theory, Galois coverings are used to study the relationship between a graph and its automorphism group. Algorithmic approaches. Various algorithms and mathematical techniques are used to find graph coverings, depending on the specific application and requirements. These may involve combinatorial methods, group theory, or spectral analysis. In summary, graph coverings are a versatile concept in graph theory with applications spanning multiple domains, including network design, coding theory, topology, parallel computing, and cryptography. They offer insights into the structure and connectivity of graphs, making them a valuable tool for solving practical problems. Artificial intelligence (AI) plays a crucial role in optimizing data for various applications, including instrumentation physics, food security, and energy sustainability. Here's how AI can contribute to data optimization in each of these fields. 1. Instrumentation physics. Data analysis. AI techniques such as machine learning can analyze large datasets generated by scientific instruments quickly and accurately. This helps researchers identify patterns, anomalies, and relevant information in their data. Signal processing. AI algorithms can enhance signal processing tasks, improving the quality of measurements and reducing noise in data collected from instruments. Automation. AI-driven automation can streamline experimental processes, reducing human error and optimizing data collection and interpretation. Point 2. Food security. Crop monitoring. AI-powered image analysis and remote sensing can monitor crop health, detect diseases, and estimate crop yields. This data optimization aids in better crop management and food production. Supply chain optimization. AI algorithms can optimize the distribution of food resources, minimizing waste and ensuring that food reaches areas in need more efficiently. Predictive analytics. AI models can predict food security issues by analyzing factors like weather patterns, economic indicators, and population growth, allowing for proactive measures. 3. Energy sustainability. Smart grids. AI can optimize energy distribution in smart grids by analyzing real-time data on energy consumption, production, and storage. This improves the efficiency and reliability of energy systems. Energy management. AI-driven energy management systems in buildings and industries can optimize energy usage by adapting to demand and optimizing resource allocation. Renewable energy. AI can enhance the performance of renewable energy sources like solar and wind by predicting energy generation, optimizing operations, and improving grid integration. In all these fields, AI can help optimize data by handling big data, AI can process and analyze vast amounts of data quickly, identifying trends and insights that might be challenging for humans to uncover. Automation. AI can automate data collection, cleaning, and pre-processing tasks, reducing the time and effort required to prepare data for analysis. Prediction and optimization. AI models can predict future trends and optimize processes based on data, leading to better decision-making and resource allocation. Overall, AI is a powerful tool for data optimization in instrumentation physics, food security, and energy sustainability, enabling more informed and efficient decision-making in these critical areas. The statement you've provided, if a connected graph G has a finite planar covering, then G has a two-fold planar covering, is not generally true. In other words, it's not a valid statement in graph theory. A finite planar covering and a two-fold planar covering are not equivalent concepts, and the existence of one does not necessarily imply the existence of the other. A finite planar covering typically means that you can cover the vertices and edges of the graph with a finite number of planar graphs, without specifying how many times each edge is covered. A two-fold planar covering would imply that each edge of the graph is covered exactly twice, which is a stricter requirement than a finite planar covering. It's possible for a connected graph to have a finite planar covering without having a two-fold planar covering, and it's also possible for a connected graph to have a two-fold planar covering without having a finite planar covering. If you have a specific theorem, conjecture, or context in which this statement is used, please provide more details, and I can offer a more specific response.
Wow, that's amazing. Thank you, Dinayah. You explained it clearly so that I could understand the material given at the Smart Icon seminar last week.
You're welcome, Lizzie. Whenever you need it, I'll explain again.